At 1:47 p.m. Eastern Time on March 15, 2018, a massive concrete pedestrian bridge collapsed across Southwest 8th Street in Miami. Reflecting on the disaster, National Transportation Safety Board Chairman Robert Sumwalt observed that the errors up and down the line mirrored the physical collapse of the bridge itself. In seconds, the 950-ton structure crushed multiple lanes of active traffic beneath it. The ensuing investigation centered on a single troubling question: how did a team of engineers, inspectors, and contractors document a structural failure in slow motion over 19 days, yet conclude the bridge was safe? This disaster resulted from a methodical breakdown in safety verification that allowed weeks of documented distress to escalate into a total collapse. To understand the failure, we have to look at the bridge's geometry. It was designed as a single-plane reinforced concrete truss. The horizontal deck and the top canopy were connected by only a single row of central diagonal struts. Most standard bridges are built with load path redundancy. They have multiple support columns or parallel trusses, meaning if one connection fails, the physical forces distribute safely through alternative pathways. A non-redundant structure lacks these physical backups. The failure of a single connection point instantly compromises the entire system. The Institution of Civil Engineers noted this specific single-plane concrete truss design had no precedent. It was highly unusual for a structure of this scale. Because the design offered no alternative load paths, the documented cracking served as a final, critical warning of imminent system failure. On March 10th, crews utilized the accelerated bridge construction method to transport and set the main span into place. Lifting the span off temporary supports and transferring it onto its final end piers drastically shifted the internal stress distributions across the concrete members. The highest concentration of these forces funneled into a specific structural intersection known as Node 1112, where the primary diagonal strut met the horizontal deck. The integrity of this connection relied on its interface shear capacity. This is the physical ability of the concrete joint to generate enough friction and resistance to keep the diagonal member from sliding horizontally off the deck. FIU bridge engineers made a foundational mathematical error when calculating the physical forces acting inside Node 1112. The NTSB determined that the actual load demand pushing against the node was approximately double what FIU had calculated. While underestimating the destructive load, the design team simultaneously overestimated the concrete's ability to resist it. FIU erroneously applied a redundancy factor of 1.0 to their calculations, a mathematical assumption strictly reserved for structures that possess backup load paths. Before the heavy lift vehicles ever moved the span over the highway, the baseline physics dictated that Node 1112 lacked the structural capacity to support its own weight. The bridge began manifesting physical evidence of this mathematical failure on February 24, opening a 19-day window of visible distress. Crews captured photographic evidence of an initial structural crack forming directly in the white concrete of the nodal region. Following the bridge transport on March 10th, the deterioration accelerated. The concrete at the base of the node began severely spalling, ejecting debris and cracking deeply. Structural engineers distinguish between common microscopic curing cracks and the massive, deep-seated distress observed at the FIU site. By the final days, the documented fractures were 40 times larger than the standard acceptable limits for a structure of this type. Despite the severity of the damage, FIU's lead engineer, W. Denny Pate, left a voicemail on March 13th, explicitly stating that, from a safety perspective, they saw no issue with the cracking. The bridge provided undeniable physical data of its own imminent failure, but the highly trained experts reviewing the structure repeatedly misinterpreted the warning signs. In structural engineering, independent peer review serves as the primary defense against internal design errors. However, the Florida Department of Transportation had not qualified the assigned firm, Louis Berger, to conduct peer reviews for this specific, highly complex concrete bridge design. On the ground, as the concrete continued to fracture, the project team failed to enact standard operational protocols to halt traffic on Southwest 8th Street. The inspection firm, Bolton, Perez & Associates, possessed the contractual authority to mandate a road closure. Instead of acting independently, they deferred to the design-build team's judgment. A culture of professional deference replaced rigorous independent verification. stripping away the project's procedural safety nets one by one. At 9 a.m. on the morning of March 15th, the key project stakeholders convened to address the worsening damage. Representatives from FIU, FDOT, FIG, MCM, and the inspection firm were present. Following a presentation by the design engineers, the room reached a fatal consensus. The cracks were not a safety concern, and structural integrity was intact. To remediate the cracking, the team decided to adjust the tension on the internal steel post-tensioning rods located inside the failing diagonal member. This process of retensioning effectively forced massive additional compressive stress directly into a joint that was already fracturing under its existing load. At 1:47 p.m., work crews on the canopy were actively manipulating the loads on member 11. The sudden influx of pressure overwhelmed the joint. Node 11/12 completely lost its bearing capacity and violently deformed. The very action authorized to repair the bridge acted as the physical catalyst that shattered the underdesigned node. The NTSB concluded their investigation by determining the probable cause of the collapse with the severe load and capacity calculation errors made by FIG bridge engineers. FIG presented a counterclaim through the engineering firm Wyss, Janney, Elsner Associates, arguing an alternative theory for the node's failure. They asserted the fracture originated primarily because the surface of the concrete construction joint was not intentionally roughened by the contractor prior to pouring. The NTSB rejected this as the root cause. They demonstrated that even if the joint had been perfectly roughened to specification, the connections still would have failed due to the sheer magnitude of the mathematical demand errors. Regardless of the specific microscopic origin point of the first fracture, the structure simply lacked the inherent physical capacity to survive its own blueprint. The NTSB published 30 distinct findings. Among them were urgent calls for updated redundancy guidance in concrete bridge design and stricter verification of qualifications for independent peer reviewers. The Institution of Civil Engineers highlighted a critical procedural lesson. Whenever significant safety concerns arise during construction, the engineer of record's judgment must be subjected to an independent, multidisciplinary review. These professional oversights carry a permanent human cost. When the bridge fell at 1:47 p.m., it resulted in 6 fatalities. This video respects the families affected. It is documentary content based on the NTSB, OSHA, and ICE official records, and the voiceover is AI-generated. As modern infrastructure demands increasingly complex designs, the engineering industry faces a persistent challenge, ensuring that the pursuit of rapid innovation never outpaces the unyielding laws of physics and the necessity of independent